Okay, we're looking more at chapter 2. Chapter 1 test I'll put out later on today. So it'd be due a week from today. Now we looked at just to refresh your memory this example here where they prove this. That's what they're going through and verifying this. So they start with the more complicated side. Remember the plus here? I'll say plus, but that refers to our or. So how you really read that is it's x or x. But we rewrite this, the x or x plus x, we can put a times 1 beside it because of postulate 2b. Postulate 2b says, and you can read this going from the right side to the left or left to the right, either way. But it says if you start with x, if you start with anything, you can always put what looks like a times 1 beside it. That times is and 1. So that's why we can put that there. Then we look for something where this 1 is equal to. Well, from postulate 5a, 1 is equal to x or not x. Again, x plus not x. Or there's another one down here, theorem 2a, where 1 is equal to x plus 1. Now, the idea is you just use postulates if you can. If you use theorems, you should have proved those before these. So you can't use an unproven theorem, basically. So on this, back there. So this one, we rewrite 1 as x or not x. So that right there. And then at this point, we're looking for, remember, two together here, where the first item in each is the same. And so when we look down here, we found this one, postulate 4b. And remember from last time, we then rewrote it. The first is x, and that stays x. And then the second part's the y and z put together, but like that. So here, since these were the same, x and x, it stayed x, my first part. And then the second part here, this x and this not x, we put together right here. And then there's a plus or an or between them. Then remember we had x not x equal to 0. That was postulate 5b right here. And then you can drop the 0, not just because it makes sense. You have to cite something. This one right here, postulate 2a, says if you have a plus 0, plus is again or, then you can just drop that plus 0. Okay. Now, this one here, I don't think we looked at this one. We looked at the one we just referred to last time. But here you start out with your x and x times x, and you're trying to think how can I rewrite that? That's kind of the hard step on some of these. I come down here, I'm looking for something I can put beside it. And see, I might be challenged. Do you put a times 1 or do you put a plus 0? I can't think of anything else where I guess you can repeat itself. See how this is x and x or x or x? So I guess you could repeat it. So you got x and x, and then there's a plus and x times x again. But anyway, they chose 0. Sometimes it's trial and error. I don't see which ones to choose right away. Then 0 from postulate 5b is equal to x and not x. That's where the x and not x comes right here. And then at that point, two items multiplied with a plus between it. And the first is the same in each. X 5b. Postulate 5b. Oh no, 4a. 4a is what I'm should be. 4a. Where's 4a? Postulate 4a. Okay, going backwards. I see it now. No, oops, we started with that. So if you start at the right side, we got xy plus xz. So xx plus x not x. So the x's are the same. Okay. So going backwards on 4b, that says that since the x is the same in the front of both of those, that goes out front here. And then the y and z you put inside of the plus between them. Okay, so that's where they get that. And x or not x is equal to 1. That's from postulate 5a. And then I'm looking to get rid of that 1. So from postulate 2b, it says if you have an and 1 or a times 1, you can just drop that. And so that's where they get that. Let me try this one. I'm not very good at these. I can simplify them, but to prove some of these theorems and so forth is challenging for me. So we're trying to show that x or 1 is equal to 1. And I'll cheat if necessary. Always start with the harder side. I think that's best way to go. Now, probably, I'm going to try to stick with postulates since we haven't proved all the theorems. I'm probably going to rewrite to 1. And 1. I can rewrite this way. 1 is equal to x or not x. That's one possibility. 1 is also equal to x plus 1. I'll refer to them as pluses and times just for simplicity's sake. Is that it? I guess that's it. Okay, so what do I want to do here? Probably since I had x plus 1 originally, I probably don't want to use that one, I'm thinking. So I'm going to choose this one. X or not x. So x plus not x. And that was, what was that? That was postulate 5a. That allowed me to do that. Now I'm looking for a variable here and 2 variables inside, and maybe that this is the same as this. I don't know if that means anything. That's a theorem. I can't ignore that. Two items inside the parentheses. Oh, here. Distributive. We got an item out in front. Well, that's a plus. Never mind. Oh, that's theorem. Can't believe I'm stuck already. Since there's a plus, I suppose those parentheses shouldn't even doesn't have to be there. I wonder if that would help us. That's not really a postulate. Parentheses aren't necessary if this is a plus. So how about if I focus, I think I got something that's x or x plus x from, that's a theorem. Shoot. Okay, I want to look at theirs. I didn't get very far. You just can put a 1 there. They left the 1 alone. I wouldn't have thought of that, but I wasn't going anywhere with what I was doing. Okay, so let me just use that hint, see if I can go from there. Okay, so what do they do? Put a 1 out in front. Okay. Thanks. That'll help me in the end. Okay. Now that's from, you just put a 1, and it's commutative, so that they put it on the front doesn't matter, but that's from postulate 2b. If I had to guess, we're probably going to rewrite the 1. Geez. And 1 was equal to that, or 1 is equal to that. And that's one that's a theorem, so that's one we're trying to prove. This is a postulate, so that'd probably be a good, that's the only one with 1 on it that isn't a theorem. Well, that pretty well narrows it down. This has to be rewritten in this manner. Now, whether you put a times there or you put parentheses next to each other, same idea. And that was from postulate 5a. Now we're looking for two parentheses next to each other where they have the same item, same first item. Postulate 4b looks like it. I don't see anything else that would even come close. Postulate 4b. That says that postulate 4b right here. That says that they both start with x, so x comes here. These both start with x, so x comes here. Then we have a or plus. And then it looks like we take the y and z and put them next to each other with multiplication or an and between them. So we're going to take the not x and 1 and put a multiplication or an and between them. Okay, I bet that the 1 disappears from this, going the other direction, postulate 2b. You can just drop the 1. And I'm hoping it's something that says that x plus not x is equal to 1. Postulate 5a says x plus not x is equal to 1. So 5a, which is what we're trying to show. That would have took me a while just to realize that I just put a 1 out in front like that, and that's where I needed to head. I was focusing on this 1 right here. Okay. They pretty much do the same thing. Okay, yeah. Probably embarrassed myself enough for those. Let me do one more. me do this one. Trying to show that x plus xy. And again, keep in mind, that's not what that actually says. That says x or x and y is equal to x. But it's just simpler to think of it that way. Always start with the harder side. Hopefully this isn't one where I had to put a times 1 in front or something like that, or a plus 0 at the end. But we'll see. I'm looking for two things that are have a plus between them. And this is a single item. This is a single item. And they're the same. Okay. And let me just make this a little bit easier. That's gone. That's gone. That. 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 And that. Okay. So x plus xy. X plus xy. I mean, now you can get step one. Okay, cheating, step one. Never thought of that in 10 years. So put a times 1 with the x. Okay. So just automatically put a 1 with something based upon postulate 2b in terms of multiplication or and. Okay, so now I'm looking for two things multiplied together or anded with an or between them, a plus. So this one, xy plus xz. The x's are the same. Going to the left side, looks like I can put the x out in front and y plus z in front. Kind of like a regular distributive property from college algebra. So take that, put that out here. And that's from postulate 4a. Um, 1 plus. 1 plus. I can rewrite the 1 as this, although probably make more sense if I rewrote it as y's instead of x's. What if that would help? Let's see. So I could rewrite that as y plus y prime, then the plus y carries down. And that's from this one right here, postulate 5a. Um, Okay. Let's see where I could cheat. I could have these printed off and have them beside me, but I wanna be honest in what I do here. So, um, okay, let's see. 1 plus y, I got that. Then they flip them around. Okay. Wasn't even headed down the right path there. And that's the commutative property, which is flip them around because of postulate 3a. But then, how in the world did they rewrite this as a 1? Y plus 1. Ah, it is a theorem. So they used a theorem, didn't they? Okay, I guess I shouldn't have crossed that out. So I probably would have never been able to solve it with postulates. Yeah, you're right. Because let's see. Because this right here says if you got x or 1 or x plus 1, that's always equal to 1. So yeah, you're right. They got rid of it because of that. That's theorem 2a. And then the times or and. When you and a 1, what's it do? Gets rid of the 1. So that's from postulate 2b. Now, the reason why they could use that theorem is because I'm sure they proved it up above. Again, the idea on when you're doing proofs is you can't use an unproven theorem. But if you prove it, then you can use it from then on. So, anyway, now it's here. Got this theorem here. It says the theorems of Boolean algebra can be proved by means of truth tables. In truth tables, both sides of the relation are checked to see whether they yield identical results. So if you go through here, and let me actually show that. It's not a kind of conventional proof like you might be used to. If you've seen proofs at all, probably geometry would be maybe where some people have seen them. But if you go through and you test all of your cases, there's nothing else to do. So 0, 0, 0, 1, 1, 0, 1, 1. Now, this right side is x. So this would be right here. So we got what that looks like. So now we're trying to get this. So first thing I'm going to do is the x or y. And remember, you add it. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. This is a weird one. You got 1 plus 1, which is 2. So it's what? I think 1. Remember, I didn't say. Okay. We'll check. Now you take the x column times the and the x plus y or x or y column. 0 times 0 is 0. 0 times 1 is 0. 1 times 1 is 1. 1 times 1 is 1. Now, if you compare this one against the one we just found, see how they both have the same results? That proves this via truth tables. Now, I'm pretty good at these. I'm not so good at maybe taking this and applying the properties. And it's like they're showing you how they do the different theorems, where you build it, and so forth. Again, you take in pieces. Like here, De Morgan's theorem, they're focusing on left side first. So you got x or y. So you got a column where you got x or y. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. Then it applies this to, or tilde, or apostrophe there, prime. That's a not. And not flips these to the opposite. 0 becomes 1, 1 becomes 0, 1 becomes 0, 1 becomes 0. And now this is the left side. So then we start a new column focusing on the right side. So we come up with a not x, which is just the x is flipped, 1, 1, 0, 0, 1, 1, 0, 0. We come up with y prime, which is the y is flipped, 1, 0, 1, 0, 1, 0, 1, 0. And then there's an and between or multiplication. 1 times 1 is 1, 1 times 0 is 0, 0 times 1 is 0, 0 times 0 is 0. And this x prime, y prime is the right-hand side. So our left-hand side was this column right here, and that's our right-hand side, and you see they're the same, which proves De Morgan's theorem. Then you see here, they say the algebraic proofs of the associative law and De Morgan's theorem are long and will not be shown here. However, the validity is easily shown in truth tables. Okay. Operator precedence for evaluating Boolean expressions is parentheses first, then the not, then the and then the or. Now here's a practice problem. We got this right here. We want to simplify it using the basic theorems of postulates of Boolean algebra. So let's take a look at that. Some of these take me a while. I get them eventually, but so there's no time limit on the second test on this. X prime, y prime, z, x prime, y prime, z, plus xyz plus x prime, yz plus x, y prime, z. Now these, you can imagine these are all circuits. So there's AND gates in here, there's OR gates, there's 3 OR gates. There's 1, 2, 3, 4. Well, no, you can do this all in one AND gate. 1, 2, 3, 4, 5, 6. There's 7 gates in there. If this was a circuit you were designing. Now, one thing to notice is that x plus x prime is equal to 1. Now, it doesn't matter when we're talking about x. It could be y. Y plus y prime is equal to 1. Z plus z prime is equal to 1. So if you can get the primes together, then they can cancel each other out. Now, I notice that this term and this term both have a yz. So I think that I can rearrange it in this manner. And that's the commutative property where you can flip things around. That's postulate 3a that's allowing me to do this. And at the same time, I can put these two together because they both have a y prime z. And there's probably many ways to simplify this. So do not think that I'm showing you the only way. This is just what's jumping out at me. Okay, now if I focus on the first two terms, I notice they both have a YZ. And notice that postulate 4a says xy plus xz is equal to x times y plus z. This says if they have the same item, they both have an x, you can think of it as factor the x out. Well, they both have a yz, so I can factor that out. Now you might be sitting there and saying, whoa, wait a minute. How can you do that? This is a single letter here, the x. Here, these are two letters. Well, remember, a single x in terms of our truth tables gives you 1 or 0. When you do y and z, y times z in a truth table, it just gives you 1 or 0. So this can be thought of as just single value, which we can bring out. Now over here in this grouping, they both have a y prime z, so I can bring that out. And that leaves me x prime plus x. And again, that's our postulate 4a. I kind of got off a little bit on the alignment. Now, x or not x plus x prime is from postulate 5a equal to 1. So postulate 5a, that's going to be yz times 1 plus y prime z times 1. Now, I think there's something that says that 1 can be dropped off. That's postulate 2b. So this becomes yz plus y prime z. Well, the same principle that we did up here, where they both had the same value under this, and we factored it out. These both have a z, so I can bring a z out. And that leaves me y plus y prime, or y or not y. And that's postulate 4a again. So I can factor that out. Then y or not y from postulate 5a is 1. And then we can drop the 1 from postulate 2b. So this says if we had all those gates, then it's as simple as just having a wire come over from Z. And X and Y don't matter. So we can eliminate seven gates in our circuit design. Does that make sense on what I did there? It just takes playing to get those. Like I say, I can go from something more complicated and go to something simpler like that. Just willy-nilly putting a 1 in just throws me. And what's this say? Develop a truth table for the Boolean expression. Let me try that. Okay, x, y, z, and where are we headed? X prime, y prime, z. X prime, y prime, z. Probably won't get these in the same order as what they do, but I'll get all of them listed. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Now, not X. That means I just flip these X's. So that's 1, 1, 1, 1, 0, 0, 0, 0. Not Y. I'm going to flip the Y's. So 1, 1, 0, 0, 1, 1, 0, 0. Now, of course, we had our order of operations, what takes precedence and so forth. So after I got that, I'm going to first do this. So X prime, Y prime. Again, how that's read is not X and not Y. I'll multiply these together. 1 times 1 is 1. 1 times 1 is 1. 1 times 0 is 0. 1 times 0 is 0. 0 times 1 is 0. 0 times 1 is 0. 0 times 0 is 0. 0 times 0 is 0. And then X prime, Y prime, Z, which is the F they're referring to, would be to take this column and multiply it times this column, because there's an and there. Again, how that's read is not X and not Y and Z. Okay, 0 times 1 is 0. 1 times 1 is 1. 0 times 0 is 0. 1 times 0 is 0. 0 times 0 is 0. 1 times 0 is 0. And I guess the rest of these are zeros. So assuming I's didn't get off, they shall be zeros except 0, 0, 1. 0, 0, 1. That's the one. Now, part of it, and this I really am bad at, part of this is some people can look at this and say, oh, well, that's equal to X plus Y or something like that. They can look at this and see that it's equal to something. It's not, unless I just got really lucky. I can maybe look for patterns and see it, but I don't see it very often. They don't really show that here, but to build that, you can come up with columns like what I showed. It's really hard to go from this directly to the answer. And that's it for that section. Okay, section 2.5 deals with Boolean functions. It says Boolean algebra is an algebra deals with binary variables and logic operations. Boolean function described by an algebraic expression consists of binary variables, constant 0 and 1 logic operation symbols. For a given value of the binary variables, the function can be equal to either 1 or 0. As an example, consider this Boolean function. It says function f1 is equal to 1 if x is equal to 1, or if both y prime and z are equal to 1. It's equal to 0 otherwise. And you can build a truth table to see this. So it's not that you should be able to look at this and immediately see that unless you're just super great at that. Let me show that. We got x and y. And 0, 0, 0, 1, 1, 0, 1, 1. Now the prime takes precedence first, so I'm going to find that. Not y is flipping all those, so that's 1, 0, 1, 0. Then the multiplication or the and takes precedence next, so that's why I'm going to find this y prime z. So I'll multiply z. I didn't even see that. Let me try that again. Blind, I guess. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And what we had? Y prime 1, 1, 0, 0, 1, 1, 0, 0. I just flip all the y's. I need y prime z. So I'm not saying it again. That's not y and z. It's how you read that from a logic standpoint. But I'm going to multiply these two columns together. 0 times 1 is 0, 1 times 1 is 1, 0 times 0 is 0, 1 times 0 is 0, 0 times 1 is 0, 1 times 1 is 1, 0 times 0 is 0, 1 times 0 is 0. I'm going to double check myself. Okay. Then our next is the x plus. Again, that reads x or not y and z. But that means we're going to take this column and we'll add it to this column, taking into account of our weird 1 plus 1. 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 0 is 0, 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 1 is 1, 1 plus 0 is 0, 1 plus 0 is, what am I doing? Let me double check that. 0, 1, 0, 0, 1, 1, 1, 1. Okay. So going back to see what they're referring to. It's equal to 1 if x is equal to 1. See if that's true. Yeah, they're all equal to 1. Or if both y prime and z are equal to 1. Y prime and z are both equal to 1, which is this case right here. So yeah, that's true. And then 0 elsewise. And this is our f sub 1. Now here, they go through, they don't show all the steps, but you could build it for F1, and what in the world's F2? We're going to talk about it down below. Okay, the F2 that they're referring to is this one down here. So it'll take a few more columns to get this. I won't show that. And then they're showing how you can then implement that, taking into account your what takes precedence. So let me show that. Next time I'll be introducing a software package where we can write that. Or not write it, but we can design it. X plus y prime z. The book will always do these neater than me, but you got 3 inputs coming in. You got x, y, and z. Now, y is going through an inverter. Y prime is an inverter, that's a not. That flips it to the opposite. So if it's coming in as a 1, it'll flip to a 0. If it's coming in as a 0, it'll flip to a 1. Then that's coming in with z into an AND gate. Now, our AND gate look like that. So this is our, this gives us our y prime. This gives us our y prime z. That then is coming in with the x into an OR gate. I can't draw very well. And then this is going to give us our output. And from a design standpoint, if we were designing it, the fact that when x is 1, when x is equal to 1, then our output's always equal to 1. That could be like a switch or something. We turn on this. I'm thinking in terms of like a house. Though we're definitely at a circuit level, we don't think of it in those terms. I'm just trying to put it in something we can relate to. If you flip that on, then this will automatically be turned on here, no matter what. No matter what's going on down here, if this is turned on, then this will be on. Now let me do that other one. The other one for a logic diagram. Oops, don't put down that far. There it is. F2 is equal to x prime y prime z plus x prime yz plus xy prime. And it doesn't matter how you do these. I've seen some that will put the the inputs up here at the top. It's kind of whatever your choice is, like x, y, and z. And then if they're going to use x prime, y prime, and z prime, and I don't see a z prime, but if they're going to use those, they have x coming down, and they have it coming down like this. They have y coming down like this. They have z coming down like this. And for those that have an x prime, they have this coming off to an inverter. And that'll give us our x prime coming down. And they have y coming off to an inverter. And that gives us our y prime. So then over here, we need x prime, y prime, z, and that's in an AND gate. What did I say? X primes, we have a line coming over like this. And I didn't have that come down. So that's coming in there. We have y prime. That's coming into our AND gate. And we have a z coming into an AND gate. So this is our x prime, y prime, z. Now we got another AND gate here. And what's coming into it? X prime, which is over here. We have a y, which is coming in over here. And we have a z, which is coming in from here. And this is going to be our x prime, y, z. And then our last AND gate. And remember the order of precedence here. We do our ANDs before we do our ORs. That's why I'm doing these multiplications. We got x, which is clear over here. Shouldn't have done that. Those don't actually meet. So we have our x coming in there, and we have y prime. Okay, now these come into an OR gate. That's what the plus is. So we have an OR gate. I can't draw it real well. So we're going to have this one coming in. We'll have this one coming in. And we'll have this one coming in. And this is going to be our x prime y prime z plus x prime y z plus x y prime. And then that's going to give us our output. So all that's going to come down to giving us either a 1 or 0. So no matter what our input's coming in, that Boolean function is going to be 1 or 0. Now let's take a look at how they did that. Yeah, that was a lot neater than mine. But you get the idea. X has to be flipped to an inverter. Y has to be flipped to an inverter. So that's X prime coming out here, Y prime coming out of here. You follow lines to see what it is. That's kind of interesting sometimes to go backwards from your logic your logic gate diagram here and come up with the original Boolean function. Anyway, does that make sense on how to create one of those logic diagrams? And why do they have that? Does this simplify? They got F2 here. It does simplify. Okay, because if I go through here, then I got x prime, y prime, z plus x prime, yz plus xy prime. If I look at these first two, they have an x prime in common. They also have a z in common. So I can factor those out. Now that's from the distributive property going backwards there. That's postulate 4a. Then y prime plus y, I could flip it around, but basically if you've got an or between them, an add, that becomes a 1. And that's from postulate 5a, right? Yeah, postulate 5a. And a 1 disappears. And that's from postulate 2b. And I don't see anything else. Maybe that's a simplified version. xy prime plus x prime z. I have it flipped around, but commutative property allows us to do that. So this is the simplification of that. So you see that we still have 2 inverter gates. We haven't got rid of those, but we took our three AND gates down to 2 AND gates, and we still have an OR gate. And you might say, well, big deal, how much difference does that make? Well, again, we're multiplying this. These are microscopic. You can't see them with your eye. And you multiply this times 200,000 of these that you're implementing in your circuit, and all of a sudden that one getting rid of that one AND gate is quite a bit of savings. By the way, this is a typo here. I'm assuming the book isn't like that, but the circle should be at the end of that. It's not separate. Okay, that's one we just did. It's obvious that the circuit in B is simpler than one in A, yet both implement the same function. By means of a truth table, it's possible to verify that 2 expressions are equivalent. So that's one thing. If you were doing this from a design standpoint, and you weren't using some automated tool to simplify it, you could do a truth table and verify that what you had originally is equal to your simplified form right here. That'll tell you if you did everything correct. Let's see. Same outputs, each circuit implements same, but the one with fewer gates and fewer input to the gates is preferable because it requires fewer wires and components. I don't think I even noticed that there was fewer wires. I guess it'd have to be fewer wires because you don't have 3 coming into here, you only have 2. Okay, that's obvious. I'll wake up eventually. That's probably not a bad place to stop, because I'm not going to get through these. I want to go through and do these 5 examples without just saying is true. I want to simplify it so we see how to use those properties. It goes back to that same property page. So next time we'll pick up where we left off here with algebraic manipulation. Well, have a good day.